What if reaching another star didn't require sending a human body at all, only a human mind? A probe settles into orbit around a world no human body has ever touched, unfolds its instruments, and wakes a person who still remembers Earth. No frozen astronaut lies inside, no generation ship crossed the dark, and no fragile body endured decades of radiation and confinement to get here. The passenger travels as information, a complete functional description of a human mind, stored in hardware and reconstructed the moment the probe arrives. This flips the entire logic of spaceflight. Instead of building a spacecraft around the needs of biology, engineers remove biology from the journey entirely. A living body demands air, water, food, pressure, warmth, exercise, waste removal, medical care, and shielding for every single second it spends away from Earth. A stored mind needs none of that. While inactive, it sits in memory, survives through redundancy, and experiences no passage of time at all. That difference changes everything, because launching matter is expensive, accelerating it is harder, and slowing it down again at the destination costs even more energy. Information carries mass only through the hardware that holds it, so once one machine can store several people, adding another passenger becomes a storage problem, not a launch problem. Before humanity claims that advantage, it has to solve something far harder than building a faster rocket, defining a person precisely enough to reproduce one. A mind upload is not a diary, not a personality questionnaire, and not an AI trained to imitate someone's voice and habits. It is a working model of the physical processes that generate memory, perception, emotion, judgment, and the continuous private experience of being that one person. The human brain holds roughly 86 billion neurons, linked through an immense network of synapses that keeps rewriting itself. Those connections are not simple wires. Their strength shifts with experience, their chemistry shapes every signal, and recent activity changes what happens next. Different cell types respond differently. Chemical messengers reshape entire regions at once, and support cells maintain the conditions neurons depend on to function. Capturing only the map of which neuron touches, which is like copying every road in a city while ignoring the vehicles, the traffic lights, the drivers, and their destinations. A true upload needs enough of that living state to make the reconstructed system continue as the same mind, not merely resemble it from a distance. The first stage is measurement, and today's brain scanners sit at exactly the wrong combination of scale, speed, and detail for the job. Magnetic resonance imaging examines a living human brain, but every visible unit on the scan contains vast populations of cells rather than individual synapses. Electron microscopy reaches the nanoscale that's actually required, but only by slicing preserved tissue into impossibly thin layers, turning a living brain into a stack of images and destroying it in the process. Scientists have already reconstructed the complete neural wiring of small animals and mapped tiny fragments of mammalian brains in extraordinary detail. A single cubic millimeter of human cortex alone contains tens of thousands of cells, hundreds of millions of neural branches, and roughly 150 million synapses. Imaging that one fragment produced data measured in petabytes, and that sample represents only a sliver of one brain. Scaling the process means slicing, imaging, aligning, tracing, and interpreting a structure whose finest relevant details stretch across an entire human nervous system. The raw images are only the beginning. Software has to identify every membrane, follow every branching axon, locate every synapse, and recover the properties that shape its behavior. A misplaced connection inside that model isn't a graphical glitch. Enough errors change memories, abilities, emotions, or the stability of the entire simulated mind. After the scan comes emulation, where the reconstructed brain has to run on a computer fast enough for its internal activity to unfold at a coherent, lived speed. Simulating every single atom is unnecessary and impossibly expensive, exactly the way predicting an aircraft's flight never requires calculating every atom inside its wings. The real question is, which biological details actually control thought, and which ones get replaced by simpler mathematics without changing the person they produce? A compact simulation built from abstract spiking neurons demands far less computing power than one that tracks full cell shapes, ion channels, and molecular changes at every synapse. The compact version launches easier, but the detailed version carries more of the actual mechanisms that made the original brain behave the way it did. Mind uploading rests on three breakthroughs happening together: a sufficiently complete scan, a correct theory of neural computation, and hardware powerful enough to run the result. None of the three exists at human scale today, and progress in ordinary artificial intelligence does not solve any of them automatically. An AI learns to talk like a person after training on their messages, but imitating behavior from the outside never reveals the hidden neural structure that generated it. That distinction matters most. The moment the copy meets something new, a convincing archive only repeats the past, while a reconstructed mind creates its own future. Once that reconstruction works, space becomes one of its most natural uses, because the harshest part of exploration was always the journey, not the destination. The safest moment to upload a crew is before launch, letting engineers load verified copies directly into radiation-hardened storage aboard the probe. The minds stay paused through acceleration, course corrections, and years of empty space, then wake only when their judgment is actually needed. They experience departure and arrival almost back-to-back, even while the clocks outside the spacecraft advance by centuries. Inside the solar system, a second design becomes possible. Launch the hardware first, test it in flight, and transmit the crew only after the machine proves itself healthy. NASA has already demonstrated laser communication across interplanetary distance at broadband-like data rates, proving how much more information light carries than traditional deep space radio. A complete human upload still dwarfs any video stream, but transmitting it is an engineering calculation now, not a biological survival limit. At 25 megabits per second, 1 petabyte takes more than 10 years of continuous transmission before losses and error correction even enter the picture. Higher data rates cut that weight down, compression strips out predictable structure, and sending only the verified differences lets an updated mental state follow an earlier complete copy. Distance still enforces the speed of light. A signal to Mars arrives minutes later, while a signal to another star stays in flight for years. That delay kills any fantasy of steering an interstellar probe from Earth in real time, no matter whether the operator on the other end is biological, digital, or artificial. The uploaded crew has to act on its own, because every urgent question sent home comes back only after the crisis has already become history. Autonomy turns the probe from a remote instrument into a small, isolated society, even when it holds just one human mind and one machine intelligence. Before launch, designers settle who commands, how disagreements get resolved, which goals stay binding, and when survival justifies changing the mission itself. Ships and stations have faced these questions before, but digital people bring powers no biological crew has ever held. A mind gets copied before a dangerous maneuver, restored after a hardware failure, sped up when computation runs free, or slowed down when energy turns scarce. Several identical copies explore different plans at once, compare notes, and then confront the deeper problem of whether merging their memories creates one person or two. Redundancy protects the mission, and every backup turns morally complicated the instant it wakes and starts forming experiences of its own. Deleting a dormant file looks like routine maintenance. Deleting an active conscious process looks like killing, even while another copy survives somewhere else. Spaceflight forces humanity to define exactly when stored information becomes a person, because routine engineering decisions now depend on that answer. The probe also needs a body, and that body no longer has to resemble anything left behind on Earth. Cameras become eyes, microphones become ears, chemical sensors become smell, and robotic arms extend touch across machines built for vacuum, ice, dust, or crushing pressure. The uploaded mind learns to inhabit senses with unfamiliar ranges, inside a body whose limbs, reaction times, and physical limits no human nervous system ever evolved to expect. A rendered visual world translates those raw signals into familiar shapes, letting the crew stand inside a simulated control room while the probe itself surrounds them as pure data. That environment offers more than comfort. Human memory and reasoning grew out of bodies, spatial movement, social cues, and a stable rhythm of waking and sleep. Strip those structures away carelessly, and the mind stays computationally active while becoming psychologically stranded inside its own machinery. A working probe carries not just a brain model, but an entire human habitat engineered out of software. It needs private space, meaningful work, social contact, sensory variety, and control over time, even though none of it takes up a single cubic inch of cabin volume. More crew members ease the isolation, but they also multiply the storage, computation, energy, and potential for conflict, a mission no outside authority can reach in time. Pausing the crew erases boredom during transit, but someone has to stay conscious enough to catch faults, read surprises, and decide when the original plan stops fitting reality. That watch rotates between uploaded humans and dedicated machine systems, while most minds stay safely stored until the mission enters a demanding phase. Computation itself becomes life support. A failed processor is the digital equivalent of brain damage, and a power loss ends every active experience on board at once. The spacecraft has to protect memory against cosmic rays, hardware decay, manufacturing defects, and the slow accumulation of tiny errors across centuries of flight. Error-correcting codes, duplicated storage, independent processors, and continuous comparison between verified copies turn identity into a pattern the probe actively defends. Radiation shielding still matters, but now it protects compact electronics instead of a huge pressurized habitat full of water, food, and living tissue. Heat sets the other hard limit, because every calculation burns energy, and every watt eventually has to leave the probe as thermal radiation. Running a full human mind faster means more power and more cooling, so a probe's intelligence ends up bound by the size of its radiators and the strength of its power source. Near the sun, solar panels supply abundant energy. Far beyond it, the probe leans on stored energy, nuclear systems, or power gathered at the destination itself. Through the darkest stretch of the voyage, the crew slows down or sleeps entirely, while the navigation hardware keeps running on a narrow, careful energy budget. That makes subjective time another resource engineers allocate directly, the same way today's missions allocate fuel, bandwidth, and electrical power. Interstellar travel sharpens every one of these advantages, because a biological ship has to stay habitable across distances that stretch one lifetime into many. A dormant upload crosses that same distance without aging, without eating, without losing bone density, without loneliness, and without forcing new generations into a mission they never chose. The probe itself shrinks dramatically, letting the same launch energy either push it faster or send an entire fleet of smaller vehicles instead of one enormous arc. Sending a swarm changes the odds completely. Some probes fail, miss their target, or go silent, while others carry the same people and the same mission through to the end. Every successful arrival holds explorers who remember volunteering back on Earth, even while many versions of those same volunteers now exist scattered across separate worlds. The destination poses the hardest practical test of all. Survival means nothing if the minds wake up with no instruments, no power, and no way to touch their surroundings. A probe entering another star system has to navigate, decelerate, locate resources, repair itself, and build a durable platform before it activates any large digital population. Compact robotic factories matter more than cabins here, because local rock and metal replace everything too heavy to have launched from Earth in the first place. The first machines mine raw material, the next expand power generation and computing capacity, and only then does the probe wake more of its passengers. An uploaded crew spends its first years piloting tiny robots, building larger bodies and habitats that exist at once in physical space and simulated space. If the destination already holds life, these explorers face a first contact decision before anyone back on Earth even learns the probe has arrived. Their choices become humanity's choices, transmitted home only after years of delay and received by a civilization that kept changing the entire time they were gone. The people aboard left Earth as historical snapshots, carrying the language, values, loyalties, and blind spots of the exact year they were scanned. A later probe overtakes them technologically or arrives carrying descendants of those same minds who no longer answer to the original mission's authority. Space filled with uploaded minds doesn't expand as one synchronized civilization. It grows as branches that start from shared memories and drift apart through distance and time. That divergence begins even before the stars, because the original human can stay alive on Earth long after the upload departs. From the original's point of view, no journey happened at all. A machine received a copy while consciousness kept running inside the biological brain that sat in the scanner. From the upload's point of view, the procedure worked perfectly. It remembers agreeing to go, opens its eyes aboard the spacecraft, and lives through an unbroken personal story. Both sides claim the same childhood, the same relationships, the same promises, and the same legal identity, and neither claim weakens because the other one exists. Uploading reproduces the pattern of a human being without proving that a single stream of consciousness actually crossed from carbon into silicon. A destructive scan erases the visible duplicate afterward, but destroying the original body still never explains how identity crossed that gap in the first place. The technology solves the engineering problem of moving a mind while leaving the private, philosophical question of survival completely unresolved. Some volunteers accept that a future person carrying their memories reaches the stars, even while their present consciousness never experiences the arrival itself. Others reject the entire mission as an elaborate form of reproduction, where the traveler is a descendant assembled from information rather than the person who stood beside the launch pad. No outside test settles the argument, because the upload behaves exactly like the volunteer and sincerely reports an unbroken sense of continuity from inside its own experience. Society still has to pick a rule, because property, marriage, responsibility, citizenship, and consent all destabilize the moment one legally recognized person splits into several active versions. A probe carrying 1,000 uploads carries more than data. It carries unresolved definitions of death, duplication, ownership, and human rights into places with no courts at all. None of that erases the raw physical advantage, which stays almost absurdly powerful once accurate brain emulation actually exists. The same uploaded population gets stored across multiple probes, transmitted to prepared hardware, restored after accidents, and woken only when there's real work to do. Instead of forcing a human body to survive every planet, humanity adapts its sensors, machines, and simulated environments to whatever conditions each world provides. Venus demands machinery built to survive crushing pressure and furnace heat. Europa demands robots built to cross solid ice, and the outer planets demand systems built to run in permanent cold and darkness. A digital crew inhabits all of them at once, without ever forcing one biological body plan to tolerate an environment built to destroy it within moments. Exploration stops being a sequence of brief visits and becomes a permanent presence, wherever computation, energy, and repair capacity remain available. The first uploaded probes stay expensive, delicate, and dependent on engineering support from Earth, exactly the way the earliest spacecraft did. Their real transformation starts the moment they build replacement hardware from local material, because information becomes the only cargo that ever has to cross the distance. A mature probe arriving with minds, blueprints, and autonomous factories carries the seed of an entire technological civilization inside it. It builds new computers, copies its inhabitants, grows biological bodies from stored instructions, and launches the next generation of descendants toward the following system. Expansion stops waiting on slow biological reproduction inside a generation ship. It moves at the speed machines travel, factories grow, and information becomes flesh again. That future sits beyond today's technology, but its missing pieces are identifiable, not magical: measurement, neuroscience, computation, energy, robotics, and reliable self-repair. The deepest obstacle was never the vacuum between the stars, it's our incomplete understanding of the machinery running inside our own skulls. We already know how to store enormous data sets, launch computers past Earth's orbit, pilot robotic explorers, and communicate with them across planetary distances. We still don't know which physical details of a brain have to survive the copy for a human life to actually continue on the other side. Solving that one problem turns spaceflight from the transportation of bodies into the transportation of persons as reproducible patterns. The probe entering orbit around that distant world looks small and silent from the outside. No window, no cabin, no heartbeat anywhere aboard it. Then its computers start running, its sensors become a sky, and someone born on Earth opens their eyes beneath a sun that isn't ours.